Yeah, so hello, everyone. So when I agreed to do this talk, I initially thought that it would be entirely about notebooks, Jupyter notebooks, right, and how to use them well, and about all the different flavors of best practices of this month and so on, right? But seeing the previous presentation and what everyone else is doing, it seems that my talk might be a bit too quote-unquote unserious for this conference, but hopefully you'll indulge me a bit. So anyway, so again, I thought it would be about notebooks per se, and we'd be using the next half hour to rant about horrible version mismatch errors, or dependency hell and stuff like that. But the more I thought about it, you can probably piece together that kind of talk already from 70 other YouTube videos. So instead, allow me to pull a bait and switch here and talk about something else, right? So something that's a bit less technical and a bit more, let's say, philosophical, right? So let's start with this guy, right? So who here has heard of John Tukey? No one? Oh, very interesting. So so if you don't know this guy, so this unassuming fellow is one of the greatest statisticians who have ever lived, right? So among a long list of achievements, he invented the fast Fourier transform, though some people attribute that to Gauss a century before him. And he also coined the words bit and software. So, if you don't know this guy, you can feel free to open up your Wikipedia to his page. He has a very long list of stuff named after him. But anyway, so in 1977, so he published a quaint little book called Exploratory Data Analysis. Right, so that's really what I sort of want to talk about today, right? So what it means to use code to understand, right? So not in terms of a demonstration, but rather to talk about the principles underlying our tools. Right, so I do not plan to give a data science lecture today. After all, there's probably at least 24 people in this room who are more qualified than I to do that. And it's not really what I'm interested in anyway. So what am I interested in? So I'm really interested in how code can facilitate conversations with data. Right, so before we get ahead of ourselves, though, let's see what John Tukey has to say about the topic. Right, so for John Tukey, it's about understanding what you can do with the information you have, as opposed to measuring and confirming how well you obtained the information. Right, so this is a really important distinction, so it pays to be more concrete here. So who in the audience has seen this set of pictures? Okay, couple. Interesting. Okay, cool. So I guess it's probably all the data science people we have. But anyway, so so for those of you who are not familiar with this set of 4 graphs, this is called the Anscombe quartet. And what's interesting about them is that they all have the same set of summary statistics, right? So what does that mean? So their means and variances are equal. The correlation between X and Y are equal. And as you can see, even the regression line, right, the linear regression line is exactly the same in all 4 of them. But of course, looking at the picture, right, intuition tells us that each of these graphs tell very different stories about the underlying process that generated them, right? And so really, what John Tukey was telling us earlier is that understanding something is not just about blindly reporting means and variances and choosing the right statistical test. Those are things you do to make sure you did things right. To understand something, you have to fight it, right? So you have to talk to it. You have to have a conversation with it. If after playing around with your data, you are not surprised by anything, then you are just going through the motions. So this is really what I'm interested in, right? So what are the ways programming has enabled us to develop these pictures or these intuitions, right? That sort of tell us what's really going on with our data beyond summary statistics, right? And to figure that out, we first need to talk about a bit of history, right? So in particular, we will start with the read-print-eval loop, or what people affectionately refer to as the REPL, right? So the REPL, right, or the thing that you get by literally typing Python in your terminal and hitting enter, is actually very old, right? It's one of the oldest things we've built in computer science. And as with most things old, it started with the Lisp programming language on a machine called the PDP-1. So yeah, this is a very old machine. It was built, I think, in the late 50s, early 60s. And it still uses punch cards. So yeah, I won't go into the fascinating history of the early hackers who worked on this computer. For that, you can read this book, this really wonderful book by Stephen Levy. But yeah, the REPL, right, which again, I'm assuming everyone here is at least somewhat familiar with, was initially built in the 1960s because multiple people needed to share single computers with each other, right? So there was this thing called time sharing. These days we have user accounts, right? But at the time, one computer, one person at a time, right? So before the REPL, or more specifically, before people invented interpreters that allowed people to execute programs without compiling them first into machine-level code, right? So people used punch cards, again, to write their programs, right? So they'd insert these cards into readers, and the computer would convert the holes into electric signals. And this process usually took hours or even days if there was a long line of nerds who wanted something calculated. Now, the REPL allowed the programmer to see the result of their program as soon as the computer was done executing it, right? So I'm not sure, this is supposed to be PyCon, but yeah, the expression above is a Lisp expression or an S expression. It's really just saying plus 1, 2, 3, but yeah. So the REPL, again, allowed people to see the results of their program immediately, right? And as soon as computers got faster and more widely available, it meant that programs didn't need to be meticulously planned beforehand, right? So, you can now play with your programs, right? So you can change a small part of them, a single variable or two, and almost instantly you would see the consequences printed out in front of you. Now, the question is, so how has the REPL evolved to let us get closer to our data? Well, there is also Smalltalk, right? So Smalltalk was where object-oriented programming really got started. So essentially, Smalltalk is this programming language developed in 1972 that was centered around the notion of an object, right? So we have our modern, hyper-advanced understanding of objects now, but originally, right, at the time, an object was a thing that can do exactly 3 things, right? So the first thing is that an object can hold state, right? Which in this case is a set of references to other objects. And then the next thing is that it can receive a message from itself or another object. And then the third thing is upon processing such a message, it can pass a new message to itself or another object. Did that make any sense? Okay, cool. Yeah, I love being in a room of full of programmers. Yeah, okay. So again, well, if you're confused though, so just look at the diagram and focus on what it means, right? So it means if you change an object, right, like if it receives a message, right, so that change can propagate other changes to other objects. And all of it happens live, right? So objects passing messages to each other and reacting in real time, right? So with Smalltalk, people began modeling objects in real life, like cars or people, right? So we all know how that turned out in practice, but for the most part, the real advance here is that with objects, we now have the ability to model complicated pieces of data directly in the computer, right? So we can talk about things that would normally be relegated to an informal set of, like, I don't know, numbers or strings. Now, what about this thing? Who knows what this thing is? Okay, so presumably almost everyone, right? So yeah, this is a screenshot of Excel, right? So a spreadsheet, right? So again, almost everyone here knows what a spreadsheet is. And I dare say that Microsoft Excel is one of the crowning achievements of humanity. So yeah, those are fighting words for some people here, but let me try to justify that, right? So what spreadsheets do really well is to let users define relationships between pieces of data without having to code, right? So, I mean, sure, technically you're still quote-unquote coding by using functions, but this is hidden very well from the end user, right? Because the first and last thing that they see is just the data, right? It's just a giant table of numbers and letters. Right, so with spreadsheets, right, it's almost always clear, at least for the user, how to proceed, right? There's always some sum that you can do or some chart that you can generate, right? So this is something that neither like a raw REPL or a Smalltalk environment has, right? The passive ability of the user to be able to understand and modify what's in front of them without having to poke around first. So to me, there are several deficiencies that our modern-day notebooks have that make it harder to maintain this conversation with one's data, right? And again, before I proceed, I just wanted to say that, well, I shamelessly stole these examples from another talk titled "I Don't Like Notebooks" by Joel Gruss, which you can check out after this, but yeah, it's a very funny talk, so yeah. Anyway, so the first problem is that notebooks have hidden state, right? So hidden state, like what do I mean by that, right? Actually, yeah, before I proceed, how many people here have used Jupyter notebooks? Okay, great, so almost everyone. Yeah, for for the people who don't know what notebooks are, yeah, basically you have a bunch of like cells that you can like put like little scripts in or like little snippets of code, and then you can execute those cells one by one, and then every time you do so, like there's like a result that appears, right? Anyway, so yeah, you'll see what it looks like in the next slide. But yeah, anyway, so hidden state, right? So what does that mean, right? So for the people who are familiar with notebooks, right, like usually the expectation is that you get the state by executing each cell, right? But consider this snippet of, a notebook snippet, right? So we define the function f of x as x plus 2, right? And then define y as f of 2. So, 2 plus 2 equals 4, right? So, what happened here? All right, so first of all, this is not a inspect element. So I didn't I didn't change 5 or whatever to mislead you. But yeah, the astute listener here would probably guess correctly that there was some cell executed between the first and the second one that sort of maybe redefined the function f in some manner, right? And so this is the issue, right? So just because cells are ordered in a certain way in your screen doesn't mean that they were executed in the same order, right? So I know this is like a laughably simple example, but imagine if there was like a cell that took hours to run, so you can't just hit like restart all, to run all of the cells, right? You'd basically need to keep track of what's going on in the notebook in your head, which is something that our computers should be doing for us, right? Okay, so what is the second issue, right? So I claim that notebooks encourage bad habits. So this example is really an extension of the first. So did you know that you can use or reuse kernels between notebooks? Right? So normally that would be fine and dandy, right? Especially if there's some gnarly data set that would be expensive to reload in your memory. But look at this, right? So hidden state with absolutely no indication that it's there aside from you remembering that it's there. So yeah, I'm talking here about the difference between like notebook A and notebook B. So yeah, you initialize the notebooks like from scratch, but notebook B has a definition for A already loaded into it because they share the kernel, right? So yeah, and the thing about this is like this also works for like imports, right? So it means you can have entire libraries there that you don't even know was part of your session. Right, so, well, I can hear the hypothetical objections from the back of the room, so you don't really need to use this feature, right, if you don't have to. And the best practice here really is to save a partial state somewhere. So, if you just finished loading some huge, some huge table or a huge array of data, then and then you've processed it, right? So you should probably save that partial representation somewhere so that you don't lose it. But yeah, the thing is, right, this kind of thing is not an isolated case, right? So Jupyter is littered with hacky workarounds and footguns that are usually patched over by extensions. So footguns that are absolutely absent in a typical non-notebook Python setup. So yeah, cool. So yeah, moving on. So what is the third problem, right? So the third problem is that notebooks make it hard to collaborate, right? So what, right? Like, isn't that the entire point of notebooks, right? That they're very easy to share with other people. So let me try to corroborate that point, right? So for one, notebooks are notorious for not working well with version control, right? So you have Git, right, and you want to use it with notebooks, and then try doing git diff in notebook, and then you'll see that it's not gonna work out of the box. So there are ways around this, of course, like using Jupytext, for example. But again, this is something that you have to go out of your way to accomplish, and it's not, it's otherwise not part of the default happy path for most users. Now, if the person you got the project from didn't bother dumping their, requirements.txt in the root directory, then you're in for a frustrating hour or two getting the versions to match correctly. And if you have different hardware or CUDA versions and there's no config file somewhere, then you're also in for some pain, right? So again, none of these issues are unique to notebooks, nor are they particularly, hard to overcome once you know your way around things. But they are implicitly encouraged by the UX and the design decisions that were made to accommodate the core concept of cell-based execution. If you're using notebooks, you still have to put in a ton of effort to make your work reproducible by others. So how do we fix notebooks then? We don't. So what we do instead is to take inspiration from what they allow us to do, right? And then try to bring that back to our regular non-notebook Python experience. Right. So for example, right, so here is a tip I got from this YouTuber, Dave Ebelar from, that's like been exceptionally helpful in my own work. So if you're using VS Code or a fork of it like Cursor, go to settings and look for Jupyter Interactive, right? So you'll find a setting named execute selection. So what does it do? Well, it allows you to highlight any snippet of Python code and hit Shift-Enter to send it to a separate Jupyter instance, which is the thing on the right. So which means you can highlight variables or expressions and instantly inspect their values without fiddling around with cells. Right? So apologies for not spinning up VS Code for this because I have a healthy fear of live demos. But as you can see here, every time you highlight something and hit like Shift-Enter, the result gets printed onto the interactive window on the right. Right? So in fact, right, this interactive window has been so useful to me that it has changed how I write Python. Right? So it's led me to adopt what I call value-orientedness. So what I mean by value-orientedness is doing as much of my work inside expressions, right? So I use ternary expressions and list comprehensions whenever I can get away with it, right? So I write pure functions that take 0 to n type-hinted arguments that when given the exact same inputs, always give the same outputs. All right, so the result of any Python expression is, if I'm not wrong, always a value, and values are easy to reason about, right? So strings, numbers, functions, they never change, and so you can chain them together indefinitely without blowing up the overall complexity of your programs. Okay, so we've seen how the REPL evolved into like notebooks and how this evolution has allowed us to play around with our data in tighter and tighter feedback loops, right? And so the end result of all this talk is that we get to ask better and better questions about the stuff we want to learn about. And this process is like very idiosyncratic, right? So the danger of like having tools like Jupyter is that you can mindlessly Shift-Enter your way through a notebook without ever having to think about what is going on in the intermediate results, right? And that's a travesty, right? In the same way that it's a travesty, for example, if a kid refuses to play in a giant playground because they don't know how, right? So another thing I want to mention before we end, I stumbled upon a process while running my interpretability fellowship, right? So it's actually going on right now on the other side of Katipunan in a tiny office just across this campus, right? So in White Box, right? So we like giving evocative names to things. So we call this process excursions. But really, it's very simple. So we had this system in our last cohort where we used GitHub issues to keep track of the research we were doing in a very specific way. So let me explain, right? So the system has three moving main parts, right? So we have questions, right? So a question is a clearly defined hypothesis that carves out some portion of your research topic. So for example, it could be something like, what happens when I change this hyperparameter a certain way? Or something even simpler like, how do you train GPT-2 on an M1 Pro? right? So these questions become titles of GitHub issues, right? So each of those questions can have at most one answer in like 3 forms, right? So it could be a demonstration, which usually shows or answers like a yes or no, right? Or gives you like a yes or no. A write-up, right? Like a blog post or a report, or a prototype of some behavior. And lastly, we define an excursion as a period of time that's at most 2 weeks long, chosen to force people to scope their questions well, where the goal is to answer the corresponding question as fast as possible. And when I say fast, I mean if you can run the experiment that answers the question in an hour, that counts. Right? So when a question has been answered, well, that's the same thing as closing an issue, right? So yeah, so the point of doing this is that for each issue thread, right, like it can serve as a sprawling research notebook that multiple people can work on, right? So, and as you can see, right, so it's a way to like systematically do research that also keeps track of what everyone else knows about the topic at hand, right? So you can use the questions that other people answer in your own work. So you don't have to, for example, figure out how to install this library or how to set up this program or something like that. You know, you can just follow someone else's thing, right? So yeah, and well, one caveat or one note about this is like, yeah, we don't really want to-dos when we're doing research because we usually fail to document the motivation behind them, right? So yeah, anyway, yeah, so you might be wondering, right, like what's the point of like mentioning this system aside from, well, it being like quite neat. So it's because this kind of thing is only accessible to you if you put like reproducibility and having conversations with data front and center from the very beginning, right? So once you really push to the extremes, the ideas behind the REPL and like notebooks, you can go really far, right? So with excursions, you can turn research into a highly collaborative process by default. Right, so of course I want to mention that the initial seed of this idea came from Simon Wilson, aka the co-creator of Django, and who also happens to actively maintain over 180 open source projects at any given moment. So yeah, this was an excellent talk, and you should all take some time to check it out. Right, so now we come to the end, right? So what's next for REPLs? So Andrei Karpathy opined on Twitter recently about like something he calls vibe coding, right? So which is where you just use Composer, for example, in Cursor or something equivalent to that, right? And you basically just let an LLM write all your code for you without checking any of its work. So that might sound horrible to some people in the audience. But the fact of the matter is, frontier models are good enough to allow this sort of thing for small to medium-sized projects. And, well, I mean, I don't know if you've been keeping tabs on things, but we recently got Claude 3.7 and GPT 4.5. Well, GPT was kind of disappointing, but yeah, in any case. Yeah, so the point is, especially for like exploratory work, right? So LLMs allow you to keep making progress, full stop, right? So this is really the pinnacle of like having a conversation with your data, right? By literally having a conversation with it, right? So, and as a wise YouTuber keeps saying, well, what a time to be alive. All right, so yeah, that's it. So feel free to ask me any questions, although I probably can't take a lot because I need to get back to my office. But yeah, I hope you got something out of my talk anyway. And yeah, have fun in the rest of the conference.
Thank you so much, Clark. I think we can have a couple of questions. We have microphones over there and there, so feel free to approach if you have any question. So while you're getting your questions ready, I actually have one. So you mentioned about having conversations with data, but how do you avoid like falling into a rabbit hole or like doing too much exploration?
Right. Yeah. So this is sort of why we had to come up with the excursion system in my org. So again, so white box research, which is the organization that I co-founded. We run like research upskilling. Basically, we teach people how to interpret transformer models. Not just treat them as black boxes, but as per the name, we actually want to figure out why LLMs answer in certain ways, right? So, as for like the question, it's really a matter of like time boxing your research or your work, right? So there's this is like I don't know, like joke principle or whatever. I forgot the name, but like work expands to fill the time allotted to it, right? Does anyone know what the name of that adage is? Okay, but yeah, it's a thing, right? So yeah, if you're very strict about okay, I'm gonna spend like a maximum of like 10 to 20 hours investigating this question, then usually you get meaningful feedback and meaningful understanding of the thing in those 20 hours or so. Yeah.
Okay, thank you so much. I think we have one question here.
Yes, hello. Can you hear me?
Yeah.
Okay. So, in your last slide, I'm sorry if this sounds a little bit off tangent, but as per your quote, LLMs allows complex data inspection without coding, henceforth like the post about vibe coding. The question that I have stems from one research indicating that the usage of large language models leads to a possibility of the user to less understand their projects even more. So the question that I have is there a way to mitigate the risk of not understanding the code at all? Is it possible that I can use large language models for coding while still understanding it fully from the low-level perspective?
Right. So that last phrase that you use is unfortunate because I think the correct answer to that is that I think we just have to get comfortable with the idea that we will not end up understanding all the low-level details of what's going to happen or what's going to be built in the next couple of years. In the same way that like assembly programmers from the olden times, right? They had to let go of this idea that they had full control over the memory of any given computer. And I don't say this as a way to justify people not being lazy about using large language models, right? So what I'm saying is that there are good and bad ways to use LLMs, right? So for example, if you give it some CSV file and ask it to analyze things, right? So if you just say, okay, give me the summary statistics so I can pass my homework, then that's probably the wrong way to do it, right? But if you actually ask it questions, right, and then try to, for example, make spot checks where you verify every now and then what it's telling you by doing maybe the work yourself, right? You don't have to do it for everything, right? But maybe just for the small things so that if everything is self-consistent, then that's a much better way to actually use LLMs in your research, right? So, yeah. And I mean, this is also true for like people doing research in like all the major AI labs, right? So they already use a ton of like compute and like just generating tokens to to further the research. So yeah, it's a wild west, right? In terms of like what we can do when we have like quote unquote intelligence too cheap to meter, right? But yeah, insofar as like understanding goes, like yeah, that's still up to you, right? Like if you actively ask questions that you're actually curious about, then yeah, it's not going to be an issue for you, I don't think.
Just to make sure that I understand the answer properly. So it's as if we should treat LLMs the way we treat compilers. Like, yes, we would not understand quite some portions of it because it helps us abstract it into higher level concepts. But every now and then, we should check it to see if the data is actually matching, correct?
Sure, and I think that's more apt in more ways than one. I think eventually you will reach a point where LLMs are as reliable as compilers. But yeah, maybe not this year or the next.
Okay, that's all. Thank you.
Yeah.
All right, thank you so much. Again, thank you, Clark, for that really interesting talk.